Welcome back, students. In this video segment, we will cover section 2.2, Subspaces and Spanning Sets. We will often be considering a subset, let's say W, of a known vector space V. So in this section and in sections upcoming, I'm going to represent sets and more specifically vector spaces with what are called Venn diagrams, or something close to Venn diagrams, just diagrams that illustrate, that allow me to illustrate vectors within a vector space. So let's assume that in this rectangle I have a known vector space V, and I'm going to abbreviate V, or vector space rather, as VS. We will often be considering a subset of V, let's call it W. So in this big rectangle, we have the vector space V, and within the rectangle we have this little blob, this sort of puddle-shaped object, and it's a subset of V, and we would like to know whether that subset also forms a vector space. Well, to determine if that subset is a vector space, we would have to determine, without anything else, we'd have to determine if it satisfies the 8 properties that we studied so intensely in section 2.1 of a vector space. Okay, it turns out that there's a way of looking at only a couple of aspects of W, that's the subset W, and determine that it actually is a vector space. So let's I'm jumping ahead of myself here. Let's back up a little bit. Let's talk about what we call W, this subset of a known vector space, if it turns out itself to be a vector space. So if W is a vector space, then W is called a subspace of V. So subspaces of a vector space are subsets of a vector space that themselves are vector spaces under the same operations of addition and scalar multiplication. So let me repeat that as you get to look at it written out. So we have a definition. A non-empty subset W of a vector space is called a subspace of V if W is itself a vector space under the operations of addition and scalar multiplication from V, but they're restricted to W. Okay, so if W forms, if we have a non-empty subset of a vector space V, and that subset, I think I said subspace. If we have a non-empty subset of vector space V and it is itself a vector space with the same operations as we have on V, the same 2 operations we have on V, then we call it a subspace of V. Okay, so let's take a little bit of a look at an example. Okay, so let's let capital W equal, let's say, the set of all 2x1 column vectors with real entries. So this is a subset of R2 that we looked at really closely in section 2.1. If you don't remember that, then you should stop the video and look at the vector space R2, and you might want to, if it's been a little while, take a look at the going through of the 8 items one by one of a vector space. If you're ready, we can just continue on, or you can just continue on. So the question is W a subspace of R2? Does this subset of R2 actually form a subspace or a vector space using the same operations of addition and scalar multiplication? Well, what does this subset look like? Well, R2 is the xy plane. What is the subset of all elements of R2 that have the second component or the second entry 0, or the second coordinate 0, if you want to think of it as points. It's the x-axis. The set x0 as a column vector. Remember, we're not making a distinction between column vectors x0 and coordinates x comma 0. This is the x-axis. So the question is the x-axis a vector space within R2? Well, look at what we would need to do without anything more. We would need to see that those 8 things, those 8 properties hold true. Okay, so property 1, I'm not going to go through all 8. It turns out we really won't need to. But property 1, we need u plus v equals v plus u for all u and v in W. This is what we would have to have happen in order for property number 1 to hold. Okay, well, we would have to say something like, let u equal x comma 0 and v equal, let's say, y comma. I said comma. I'm still thinking about R2 as the xy plane. So x0 is a column vector, y0 is a column vector. Well, what is u plus v? U plus v is x0 plus y0, and we're assuming the same operations as we had on R2 in section 2.1. That's x, the column vector whose entries are x plus y and 0. These entries are real numbers, so we can flip them around. This method of proof should be automatic to you right now if you've completed homework. So all I'm doing is the first property, and that is v plus u. And it's not so much depressing, but disheartening that we would need to go through the other 7 properties in a vector space, in a subset of a vector space where we've already gone through all 8 properties. Now, we don't need to do that. Why don't we need to check this property and most of the other properties? Well, here's the answer. We don't need to check property 1, okay? Because property 1 holds for all vectors in R2. R2 is, don't forget, R2 is a known vector space. R2 is a known vector space. So all the properties, all the 8 properties of a vector space hold everywhere, and I'm emphasizing everywhere, everywhere in R2. In particular, they hold in W. So since property 1 holds everywhere in R2 and W is just a part of R2, then property 1 also holds. Okay, if you don't get that, I'll be repeating this idea very, very soon. In fact, most of the properties of a vector space hold everywhere in a vector space, so they don't need to be rechecked in a subset of a vector space. But there are a couple of properties that don't necessarily hold everywhere in a vector space. Okay, so let's take a look at that more carefully. Okay, so properties that are satisfied everywhere in a vector space V. In every subset, no matter how big or small the subset of a known vector space V. I'm going to list properties that hold everywhere, so they don't need to be rechecked. Number one. U plus v equals v plus u holds everywhere in a vector space V. So if you look at a subspace of V, I'm just basically repeating what I said a few seconds ago. If you look at a subspace, a subset of V, property number 1 has to hold there, since it holds everywhere in the vector space. 2. Property 2 holds everywhere. Property 2 is true everywhere in a vector space, in every subset of a vector space. You can add 3 elements in any order you want. We have the associative property addition. This holds everywhere in the vector space V. Property 3 does not. Property 3 does not. Property 3 says there exists a 0 vector somewhere in V. Okay, I want you to look carefully at what I'm about to say. Here's a vector space V. V, a known vector space. Here's what we're calling W, a subset. The first 2 properties hold everywhere, no matter where you are in the subspace. The third property, the existence of a 0 vector in a vector space, holds at only 1 element in the vector space V. Why only 1 element? Because we finished proving in the last section that the 0 vector is unique. There's only 1. So where is it? Is the 0 vector outside of the subset? Is it, let me do this in red. Is the 0 vector out here? Or is it in here? See, our I didn't mention any kind of restrictions on the subset of a vector space. Is the 0 vector in the subspace, in the subset? If it's not in there, property 3 won't hold. If it is, then property 3 holds. It isn't automatically satisfied that the 0 vector is in every subset of a vector space. If you're not sure about what I just said, suppose you just think about the set of real numbers. The set of real numbers forms a vector space. Now think about the subset of the real numbers, the set of all positive real numbers. The set of all positive real numbers under the usual operations of addition and multiplication, scalar multiplication, that the set of positive numbers doesn't form a vector space. The 0 vector is not in there. Okay, so property 3 doesn't necessarily hold in every subset of a known vector space, nor does property 4. Nor does property 4. Property 4 says for every vector in the vector space, let's say V, and I'm putting it outside of W. No, actually, I don't want to put it outside. For every vector V in your vector space, and now remember we're looking at W, we're at a restriction of, or a restricted subset of V. So does every element of V of W, namely this element V, does it have an opposite? Well, if the 0 vector were in W, the answer might be yes or it might be no. Is the opposite of V outside of W, or is it inside of W? So property 3 doesn't hold everywhere in a vector space. If you have a vector space and you have an element of the vector space V, opposites are in the vector space. That's the property. That's property number 4. But it doesn't say where in the vector space. So your restricted subset may bounce the opposite right outside. So properties 3 and 4 are not satisfied everywhere. In particular, they may not be satisfied in the subset W that you've chosen. 5, 6, 7, and 8. Oops, I am mentioning 7 twice. 5, 6, 7, and 8 hold everywhere in the vector space. A scalar multiple of u plus v is just cu plus cv. It doesn't matter where you are in the vector space. The scalar c plus d times v equals c times v plus d times v. That holds everywhere in the vector space. There's no mention of where this holds in a particular area in the vector space. It holds everywhere in the vector space. C times dv, property 7, equals CdV, holds everywhere in the vector space. And 1 times v doesn't care where you are in the vector space. It's just v. Okay? So the bottom line is this. We have a potential problem with our subset, W being a vector space. We have a potential problem with our subset. Where is two problems? Where is the zero vector? And where are opposites? This is still pretty good news. This is still pretty good news. This is saying that if I want to determine if I have a subspace W of V, if I want to determine if a subset is definitely a vector space, that is a subspace, then I really kind of only have to check 3 and 4. Well, it turns out that we don't even have to do that. It turns out we could replace verifying 3 and 4 with two other things we could check. Now I'm going to put these ideas in green in our little diagram. If we have, let's say, a green element u in our vector space, I would like to know where u plus v is. Not that it satisfies property 1. I already know it does because it satisfies property 1 everywhere. I would like to know if u plus v is in W or if it's not in W. Okay. I would also like to know if C times V is in W as opposed to not being in W. It turns out that if you show the two green things, if you show that if you have two elements from your subset, remember we're physically taking just a piece of a vector space. And if that vector space, if that piece, that subset is not empty, and you can show that when you take any two elements from that vector space, that subset rather, sorry about that, subset, and they stay in the subset, and that if you take any element of the subset V and multiply by any real number, any scalar, that stays in W, then those two things turn out to be enough to determine whether whether V forms, in fact, a vector space. Okay. So that's actually a theorem. That's a conjecture. I'm coming up with that idea as something that I would like to hold true. Now, just because I say it doesn't mean it's true. So this is something that requires proof, and we're going to do it. And it's not difficult. Before we prove that all we need to do to show that a non-empty subset W of a vector space V is itself a vector space, before we prove that all you have to do is show that when you add two elements in W, they stay in W, or if you take any scalar multiple of any element of W and it stays in W, then you have a vector space. Before we prove that, we need some definition. We need a definition. We need the definition of closure. Closure. For a set to be closed, let's say under a particular operation, under the operation of addition, it means that when you add two elements up from a set, they're stuck in the set. They can't get out. It's like closure means there's sort of a wall built around the subset that says that if you take any two items inside the wall, within the walls, and you add them up, they've got to stay there. If that happens, then you have what's called closure under addition. I'm going to write that down without the wall analogy, though. So W is closed under addition. Closed under addition if for every u and v in W, u plus v is in W. Okay. Or using logical symbols, u and v is in W implies that u plus v is in W. I just said the same thing twice. I said the first statement without the arrow, the implies, p implies q or whatever logical symbol. This is what it means to be closed. When you add two things up, they stay in the set. If you're not with me, relax. Let's look at a specific example. Let's let r with a little plus in the superscript or exponent position. Let's let that be the set of all positive real numbers. Let's let that be the set of all real numbers such that x is greater than 0. The set of all numbers, real numbers x, such that x is positive. So it's the set of all positive numbers. So I want to show that r plus is closed under addition. What kind of addition? Just the ordinary addition of real numbers. Okay. So let x and y be in that set, or in that subset of R. Okay, that implies that x is greater than 0 and y is greater than 0. I want to show that x plus y is in that set. Well, x plus y is in that set. Why? X and y are positive numbers. What do you get when you add up two positive numbers? What, x plus y is in R since the sum of positive numbers. Remember, we get to assume the properties of real numbers. The sum of positive numbers is a positive number. You can't get out of positive number, the set of positive numbers, by adding two positive numbers. So R plus is closed under ordinary addition. That means not any strange made-up addition like we did in the last section. Okay. So what do you think it means for a set to be closed under scalar multiplication? I think you might have the idea, but if not, I'm going to write it out. I think you should see it written out. W is closed under scalar multiplication. If for every, let's say, u in W, comma, c times u is in W. Okay, for every c, a scalar. Okay, in other words, u in W, if u is in W, that implies that cu is in W for every real scalar c. Okay, so let's take a look at an example. Example. Is R plus closed under scalar multiplication? It means again that if you take any element of R plus and multiply it by any scalar, you automatically get an element of R plus. Let's make it a little easier to digest than that. It says if you take any positive number and multiply it by any scalar, you get another positive number. You can't get out of the set of positive numbers. Now, if you think about it that way, it's obviously not closed. The answer is no. No. Example. X equals, let's say, 3 is in there. But negative 4x, which is negative 12, that's my c. I chose c to equal negative 4, is negative 12. Oops, is positive 12, rather. And, oh, no, sorry. It's not positive 12. X equals 3 is in there, is negative 12. So negative 4x is negative 12, and that's not in there. So, no. The set of positive numbers is not closed under scalar multiplication. You can get out by scalar multiplication. Get out of that set by multiplying any particular number from that set or element of that set by a negative number. You get right out. Okay. Now, remember the scalars, they don't have to be from that set. They have to be from real numbers. Okay. So here's another example, just in case. Examples. We're going to use some notation. See some notation here that's very common. Q with a little extra slash through the Q. This is the set of all rational numbers. Q, the set of all rational numbers. If for any ungodly reason you've forgotten what a rational number is, they're fractions. You're supposed to know that. Okay, so Q, you could think about as the set of all P over Q, such that P and Q are real. Oh no, P and Q, not real, are integers. And of course, Q can't be 0. That's another fancy way to say of all the fractions. Pi over 6 is not a fraction, by the way, because pi is not an integer. Very often, even us lowly professors, we say, oh, the fraction pi over 6 is not a fraction. Fractions don't have irrational numbers in it. Radical 2 over 3 is not a fraction. Radical 2 is not a real, or is not an integer. Anyways, is Q closed under scalar multiplication? What kind of scalar multiplication? The ordinary scalar multiplication, not a made-up strange one, okay? Multiplication. Or not strange, but it's just the normal multiplication of real numbers. Well, I don't think so. For the reason I just told you about pi over 6 and radical 2 over 3, I think I mentioned. Here. X equals 1/6 is in Q. It's a fraction. But I can find a scalar multiple of that gets out of that set. Pi x, that's pi over 6. It's not in that set anymore. I bounced myself. I escaped that set. I escaped the walls of that set, if you will. I don't know what you would actually physically see the walls looking like, but I found a scalar multiple of 1/6 that is not in there. So that says it's not in there. It's not an element of Q. That says that No, it's not a Q is not closed under a scalar multiplication. So no. Okay, closure properties are extremely important. Extremely important. Let's not get too lost in the definition. So back to vector space of subspaces. So back to the question. So how do we get properties 3 and 4 to be true in a subset W of V, a known vector space? Remember, those are the problem properties. They don't hold everywhere in V. So we may be forming a subset of V that doesn't have the zero vector and doesn't have opposites in it. Okay. And the answer is, if W is closed under addition and scalar multiplication, then 3 and 4 automatically hold. Okay, we're going to prove that. Okay, so this big result is in the form of Theorem 2.3 in your textbook. Let W be a non-empty subset of a vector space V. Then, W is a subspace of V if and only if, for every two elements U and V in W, U plus V is in W and C times U is in W. This is nothing more than saying, in other words, that W is a subspace of V if and only if W is closed under addition and scalar multiplication. We don't have to check all 8 properties. We know that we only have to check 2 and 3, and we don't even have to do that. 2 and 3 automatically, 3 and 4. 3 and 4 automatically hold true. This is what the theorem is saying. If we can show that the subset that we're considering is closed under addition and scalar multiplication. Proof. This proof has 2 directions. Remember the logical symbol. Remember the logical symbol A double arrow B, that means A if and only B, means 2 things. If A, then B, and if B, then A. A implies B and B implies A. We don't have to worry about the proof this way. Well, we're going to worry about it, but it's very easy. The forward direction is very, very easy. If W is a subspace of V, then the closure properties hold true. Of course they do. Of course they do. That's by the definition of the 2 properties in the vector space. By the fact that the operations of addition and scalar multiplication are defined on the entire vector space. If W is a subspace, then W is a vector space. So its properties hold. We have closure automatically. If you didn't get that, I'll restate that. I don't blame you. The sentence I formed really wasn't too good. So let's state that more formally. Let W be a subspace of V, a known vector space. Okay. That implies that W is closed under addition and scalar multiplication. This is the easy part. the two operations are defined on the entire vector space. And I'm assuming that W is a subspace of V. That means W is a vector space. Since W is a vector space, all 8 properties hold true. And since the operations of addition and scalar multiplication are defined on all of W, there's no place for sums and scalar multiplications to go to and back into the set. Okay, so we automatically get, this is not the exciting part of the theorem, we already automatically get the forward direction. The reverse direction is where we have a problem, potential problem. The reverse direction says that if we have closure under addition and scalar multiplication, then W forms a subspace. Okay, so let's let W be a non-empty subset, not subspace. We're trying to prove that. Subset of V, which is a known vector space. So here's our little diagram of, oops, I think I'd like to make a little better diagram. Here's our little diagram off to the side here. V is a known vector space. Here's W, a non-empty subset of V. I want to prove that if I know that W, the subset, is closed under addition and scalar multiplication, then W forms a vector space. W is in fact a subspace of V. Okay, so I only need to prove that 3 and 4 hold true. Why? Since 1, 2, 5, 6, 7, and 8 hold true everywhere in V. In particular, they hold in W. So they hold everywhere in W, since W is part of V. The only thing I don't know is the zero vector automatically in W? Where is the zero vector? Where is the zero vector? And where are opposites? Where are opposites? Okay. So I'm going to show that opposites are in there first. So here's a green, I'll put it as a dot. Here's the green U. Okay, so or not, I think I'm going to be a little consistent with your textbook here. Your author doesn't do a good job of this, and I keep saying that with his proofs and stuff. For some reason, some of his proofs are really not good. So let's let V be in W. I want to show that opposites are in there. That would be property number 4. Okay. Well, so let V be in there. Now I'm assuming, remember, I'm assuming that I have the closure properties. I have closure under addition and scalar multiplication. So that implies that -1 times V is in there. Okay. Why? Since, I don't want to go back to so much green here. Since W is assumed to be closed under scalar multiplication. Remember, we're proving the reverse direction. In the reverse direction, we're assuming the closure properties of addition and scalar multiplication. Okay, so V is in there. I have forced then -1 times V to be in there. I'm putting it right where it's guaranteed to be by the scalar multiplication closure property. Okay, but we finished proving, well, we proved it a little while ago, but what is -1 times V? We proved in the last lecture that that's the opposite of V. So that implies that the opposite of V is in there. That's pretty cool. Oops. That's really cool. Oops. Okay. Look at the green. I assumed that V was in there. I just proved that the opposites are in there. That's property number 3. Okay. So this implies property 3 holds. I'm sorry, that's property 4. Property 4 holds. Well, I got opposites in there. What about the 0 vector? I need the 0 vector to be in there. Okay, I need the 0 vector to be in there. So let's prove it. I'm already assuming that V is in, I picked an element V out of there. I've also shown that the opposite of V is in there. So also V plus the opposite of V is in there. Why? V is in there. I just finished proving the opposites were in there. So V plus the opposite is in there. Why? Since W is assumed to be closed under addition. We're only assuming 2 things hold true about W. Well, 3 things really. W was non-empty. And I was assuming that I have closure under addition and scalar multiplication. In the first part, again, I showed that if I take an element V out of W, the opposite of V is stuck in there. Okay. Well, V plus the opposite of V is stuck in there since I'm assuming the closure property under addition. But what is V plus the opposite of V? That is 0, the 0 vector. Okay, so I've shown that the 0 vector is in W. That's it. That's property number 3. So it implies property 3 holds. I've got all 8 properties holding by only having to show 2 things. This is a big deal. This is a very big deal for you. Very, very big deal. It cuts down the amount of work in establishing that we have subspaces formed. It cuts down the work tremendously. You don't have to show any of the 8 properties. All you have to do is show that that your subset is closed under addition. Your non-empty subset, of course, is closed under addition and scalar multiplication. Okay. Okay, I want to look at a couple of examples here before we move on. Enough of the theory for now. So let's say, let V be a vector space. Okay, is the set that only contains the 0 vector a subspace of V? Is the 0 vector just that one, the subset of V with just one element in there? is that a vector space also? Is it a subset? Well, I got to show two things. I have to show that the set that contains the zero vector is closed under addition and scalar multiplication. So let W equal the set that only contains the zero vector. I haven't said what the vectors in this vector space look like. So we're not looking at matrices or vectors from physics or numbers or points in R2 or anything. This is an arbitrary abstract vector space. With a zero vector, we're denoting by 0. Okay, that's it only has one thing in it. Well, I need to show two things. One, let U and V be elements of W. Okay, let U and V be in there. Okay, what does that imply? It implies that U had better be the zero vector and V had better be the zero vector. There's only one thing in there. Okay, well, I need to show that when you add those two things up, you stay there. U plus V is 0 plus 0. Now, you be very careful with that you don't assume that we're dealing with real numbers or any other known specific vector spaces. What's the zero vector plus the zero vector, and why? If zero vector plus zero vector is the zero vector for U and it's obvious without you thinking of the property that's holding, then you're in trouble. You've got some trouble. Okay, because then that means you're assuming properties of real numbers or the structure of real numbers, matrices, or other known vector spaces. Why is the zero vector plus the zero vector again? I'll tell you. Because V plus 0 is equal to V. V plus 0 is equal to V. Okay, that's kind of the definition of the zero vector. But the zero vector that I'm letting V equal is also a vector in there. So 0 plus 0 is the zero vector because of that property. Okay, so the bottom line is I showed that U plus V is in there. Because U plus V also has to be the zero vector, and that's the only thing in there. Okay, 2. How about scalar multiples? Let, no, it doesn't matter really what we call it. Let U be in W. Remember, W is just the set that has the zero vector in it. Okay, and also let C be a scalar. I need closure under the operations of addition and scalar multiplication. So I need to show that C times U is in there. Okay, well, if U is in there, that implies that U is the zero vector. Okay, it also implies that C times U equals C times then 0. This is not one of the 8 properties, but it is a theorem we proved. C times 0 is the zero vector. We proved it. We proved it. I think it was theorem 2.2 or something. I think it was 2.2 in the last section. Okay. And C times U is 0, and 0 is the only thing in there. So it's in there. Done. So the subset of any vector space, W, that only has one element, the zero vector, is a subspace. Subspace of W. And I've been identifying a subspace of V, sorry about that. Subspace of V. That's better. Okay, so it's kind of the smallest, it's the smallest subspace of a known vector space that's possible. You should hear that again. The smallest possible, in terms of number of elements, the smallest possible subspace of a vector space is the subspace that only contains the zero vector. Okay. Is it possible for any other subset that has only one item in it to be a subspace? No. No. I'm going to repeat that. Is it possible for any other subset of a vector space that only has one item in it other than the zero vector? No. What would be missing from that subspace? The zero vector wouldn't be in there. Okay, so every vector space has to have the zero vector in it. Okay, so let's move on. This next example, and I realize now that I hadn't paused the video, so you sat there watching me write this out without saying anything. I apologize. I meant to do this, to write out this theorem while pausing the video, so sorry about that, about the silence there. And taking note of the time here that happened here. Okay, so here's our next example in the form of a theorem. If A is an m by n matrix, if A is we start out with an m by n matrix, then the set of all solutions to the equation ax equals 0 is a subspace of Rn. This theorem is going to follow us a long way through this course, So we need to tear it apart really carefully. Okay, we're starting with an m by n matrix. Okay, so just to indicate that, I'll put that in green. And I'm saying that the equation a times x equals 0 is a subspace. What is x? A subspace of Rn. What is x and what is 0? 0 is the m by 1 0 matrix, and x is an n by 1 column vector. Okay, so this equation ax equals 0 is the homogeneous system of equations that has A, the matrix A, as its coefficient matrix. This theorem again is going to be extremely important for us, and we're actually going to call this set something more formal later. We're going to call it the null space. I'm not going to write it out. Null space of the matrix A. I won't write it out now because its name isn't important right now. But if you have a given m by n matrix, then a set of all solutions to the homogeneous system of equations where A is the coefficient matrix of that system, the solutions to that equation form a subspace of Rn. Remember, Rn has elements that look like this. x1, x2, ... They're column vectors that have n entries. Okay. So let's do this. Let's prove this. Okay. These proofs are very important for you. They illustrate the kind of mathematics that STEM majors need to be really, really up on. And it's the only reason why we're doing the proofs in an applied math class. So let's let W equal the set of all solutions to AX equals 0. Homogeneous system of equations. Okay, and let's use more formal notation. W is the set of all column vectors X in Rn such that AX equals 0. So W is part of a vector space. The vectors, the big master vector space that we're in, the master vector space that we're in is Rn. And I think your author proves that that's a vector space. But V equals Rn, that is a vector space. We showed a special case where n equals 2. We showed that R2 was a vector space. So Rn is the known vector space, and W is that subspace. It's the set of all solutions to the system of equations AX equals 0. I want to show that W forms a vector space. I want to show that W forms a subspace of Rn. That means I want to show that W itself forms a vector space. That's 8 things. Remember, we don't have to show all 8 things. We only have to show 3 and 4. And remember, we don't even have to do that. All we have to show is that W is closed under the operations of addition and scalar multiplication. Okay, well, we also have to have the W is not empty. Okay, so W has to start out by being a non-empty set. Why is W not empty? Why is the set of all solutions to a homogeneous system not empty? You really need to think about that with me. Why is the set of all solutions to any homogeneous system not empty? Because I'll help you out. I'll actually give you the whole answer, but I want to help you. I want you to think of it if you can. Because every homogeneous system has what solution? Has the trivial solution. Every homogeneous system has as a solution the element of Rn where all the elements of 0 are 0. A times 0, 0, 0. No, I'm not saying that right. W, let's just do it. Oops, not that. W is not empty since 0, 0, 0 with n entries is in W. Why? Since A times 0, 0, ... 0 equals 0, 0, 0. This is, which is the 0 vector in R. I have to be careful about this. M. Okay. A times the zero vector in Rn is the zero vector in Rm. How is he getting that? You might be thinking. A was an m by n vector. The zero vector from Rn is an n by 1 vector, column vector. So A times 0 is the m by 1. Look at m by 1. Look at the sizes. Column vector. Okay, so the W is not empty since the zero vector is in there. Why is that true? Since the zero vector from Rn is a solution. Okay, all the solutions have to be solutions to the homogeneous system. The zero vector works. Okay. Closure under addition and scalar multiplication. Pick two elements in W. What do they look like? They look like column vectors. Let's let x1 and x2 be in W. That means x1 and x2 are solutions to the homogeneous system. Okay. We need to write that out. That means that implies that ax1 is the zero matrix is 0 and ax2 is 0. Remember, W consists of all the solutions to a homogeneous system. I'm picking two elements from there. That means I'm picking two solutions from there. I need to show that x1 plus x2 is in there. Well, let's see what multiplication of x1 plus x2 by A yields. So A times x1 plus x2 is A times x1 plus A times x2, but A times x1 is the zero vector in Rm, plus A times x2 is the zero vector in Rm. The zero vector plus zero vector is the zero vector. I've shown that A times the quantity x1 plus x2 is 0. That means x1 plus x2 is a solution to the homogeneous system. That means oops. I'm mixing notation here. That means that x1 plus x2 is in W. So I have closure under addition. 2, I need to show we have closure under scalar multiplication. Well, let's see. Let C be a real number and let X be a solution to the system. Okay. That implies that AX equals 0. Why? Because I'm picking X from the subset W, which is the set of all solutions to the system. So X is going to AX equals 0. Now I need CX to be in there. Well, here's A times CX. Matrix properties. C is a scalar. I can factor that scalar out. Well, what's A times X? It's the M as in Mary by 1 column vector of zeros. C times 0 is 0. That implies that CX is in W. I have shown that that W is a subspace of the vector space Rn. That implies, that implies that W is a subspace of Rn. This is a very powerful theorem that allows us to not have to go through the 8 properties. Okay, so what I'm going to do next is get away from proof briefly and look at some examples of common vectors, vector spaces, but common subspaces. Let's consider the master vector space, if you will, the big V vector space. Consider the vector space, the set of all functions f on AB. We talked about this set in our last video segment. It's also example 3 on page 68 in your textbook. I think your author proves it. This is the set of all real valued functions defined on the interval, open interval from A to B. It's a huge set. We talked about it. I remember now. Okay. Now I want to talk about a subset of F, and I'm going to call it CAB. CAB is a set of all continuous functions from that set. CAB is the set of all continuous functions. Set of all continuous functions. Functions on the interval from A to B. Okay. Very clearly, C is inside of F. C is a subset of F and not the other way around. Not every function is continuous, but every continuous function is a function. Okay. So CAB is a subspace of FAB. Real easy to see why. First of all, the zero vector at C is not empty, since the zero vector f of x equals 0. In order to do this, you're going to need to be familiar with the example 3 on page 68. So if you're not familiar with it, you should stop the video. You really should. Stop the video and look at that example. Okay, assuming you're familiar with that example, CAB is definitely a subspace of FAB. It's not empty, since f of x equals 0 is continuous, and that's the zero vector in F. So CAB is not empty. It has the zero vector f of x equals 0. Also, addition and scalar multiplication hold true. If you take any two continuous functions and add them up, you get a continuous function. This is theory from Calc 1. So the sum of two continuous functions is continuous. That means we have closure under addition. And a scalar multiple of a continuous function, if a function is continuous, 2 times that function is continuous, 3 times that function is continuous, 0 times that function is continuous. So scalar multiples of continuous functions are continuous. So in words, that's why C is a subspace. We don't have to show properties 1 through 8. Okay, that's powerful. Let's let DAB equal the set of all differentiable functions. All differentiable functions on the interval from A to B. Again, this is a set we looked at in Calc 1, although you probably didn't think about it too often as, if at all, as DAB. A differentiable function is a function that has a derivative at every single point in its domain, has a tangent line at every single function in its open interval domain. It has a tangent line at every single point. Okay. D is a subspace of, what do you think? D is a subspace of C, A, B. D is a subset of C because every differentiable function is continuous. That's one of the first theorems that students of advanced calculus called analysis study in analysis. If you're a math major, that every differentiable function is continuous automatically, but the reverse is not true. Every continuous function is definitely not differentiable. The absolute value is continuous, but it's not differentiable at 0. Okay, so D is a subspace of C. Okay, there are other. I'm going to list all these common subspaces. Don't get too hung up on the notation and stuff. You don't have to memorize much right now. Dn is the set of all functions that have an nth derivative. Let me kind of use my abbreviated notation I did in my last set. This is a set of all functions. All functions that have an nth derivative on the interval AB. Okay, so D2 would be the set of all functions that have a second derivative in AB. They may not have a third derivative or fourth derivative, but they have a second derivative. Okay, so with this notation, so D1 of AB is just D of AB. Set of all functions that have a first derivative on AB, that's the set of all differentiable functions. Okay. A set D5 is a very restrictive set. Okay. It has guaranteed up to the 5th derivative. Okay. Okay. Dn of AB is a subspace. Subspace. Of D. Okay. D2 would be the set of all functions that have two derivatives. Well, if they have two derivatives, then they have one derivative. They have the first derivative. If y prime D2, I think I said that very confusing in a confusing way. D2 is a set of all functions that have y double prime and have a second derivative. Well, in order to take a second derivative, what do you have to first have? A first derivative. So D2 is definitely inside of, is a subset of D1 or D. Okay. Also, D3 is inside of D2, and D4 is inside of D3, etc., etc., etc. If you have a fourth derivative, that means you have a third derivative, a second derivative, and a first derivative. Okay. So what is that saying? It says that it's saying that Dn plus 1 AB is a subspace of Dn of AB. If you have an n plus first derivative, in order to get to that derivative, you had to take n derivatives, and so you had an nth derivative, but not the reverse. Just because you have an nth derivative doesn't mean you have an n plus first derivative. So Dn plus 1 is a subset of Dn. It's actually a subspace of Dn. Okay, we're not going to prove it. These are I'm just listing common subspaces. Now, Cn, again, don't get too lost in all this notation. This side trip into special subspaces is not that important. They're common subspaces we're going to be using, but it's not essentially that we obsess too much about them right now. C sub n is the set of all functions that have a continuous nth derivative. The set of all functions that have a continuous, very restrictive derivative. Not only does it have to have a derivative, it has to be a continuous derivative, a continuous nth derivative. Every time you create a set that's more restrictive, you put that set inside of a bigger, less restrictive set. Okay. Okay. So what I just said there essentially is, or leading to essentially, is CNAB is it's a restricted version of, not version of, but it's a restricted set of restricted functions that have derivatives. Is a subspace then of, what do you think? Of D and A, B. Okay. What do you think then C0 is? It is a set of functions that have a continuous zero order derivative. Well, remember from Taylor series and Maclaurin series in Calc 2, the zero derivative is defined to be just the function itself. So that's just CAB, set of all continuous functions on AB. Okay, so what do you suppose C infinity AB is? It's the set of all functions that have a continuous derivatives of all orders. Set of all functions with continuous derivatives of all orders. Okay. Okay. Here are a couple of very specialized subsets of those sets. P. These two are extremely important. These last two. P is the set of all polynomials. Okay. Polynomials have all real numbers as their domain, so they're really in C negative infinity to positive infinity. And in fact, they have derivatives of all orders, so they're really in C infinity from C infinity of of negative infinity to positive infinity. P sub k is the set of all polynomials of degree less than or equal to k. Set of all polynomials of degree less than or equal to k. I would like to give you an idea of where these sets lie in relationship to one another. Here's F, the set of all functions. Excuse me. Defined on the interval AB. Inside that set is, inside that vector space is another vector space. The set of all continuous functions on the interval from A to B. Inside of that set is the set of all functions that have a first derivative. If a function has a first derivative, then it's continuous. If a function is continuous, it doesn't necessarily have the first derivative, though. Okay. Inside D is Dn, a set of all functions that have n derivatives. Okay. Inside there, a much more restrictive set, inside there are all those functions that have continuous derivatives up to the nth derivative. And some of those have continuous derivatives of all order. And inside there, some of those are polynomials. 1 plus x squared plus x cubed minus 3x to the fourth, that kind of thing. And some of those polynomials are of degree less than or equal to k. So the smaller the set, the more restricted of a version of the original vector space FAB we get. Okay, as sort of a sub-note here, let's take a look at how the D sets compare. D, the set of all functions that have a derivative. Inside of that set is D2, the set of all functions that have two derivatives. Inside of that set, you have those that have three derivatives, etc., etc., etc. Okay. So this is how you can see that d sub n plus 1, the statement I made above, d sub n plus 1 is a subspace of d 1 less than that and AB. Okay. Now we have quite a bit of ways to go in this section. I would estimate maybe up to another hour or a little more. You might want to take a little bit of a break. Otherwise, then you can continue to power through it with me. All right, folks, let's continue. We start up the next part of this lecture with the definition of what are called linear combinations. So here we go. Let's assume we start out with n vectors from a vector space. If v1, v2, v3, all the way up to vn are elements of a V, which will be a vector space, then C1 times V1 plus C2 times V2 plus C3 times V3 plus ... all the way up to some nth C times Vn is called a linear combination. A linear combination of the vectors v1, v2, all the way up to vn. Okay, where the c's, c1, c2, all the way up to cn, are some scalars. Okay, the definition of linear combinations is not a real complicated one, even if it seems like it. For example, let's say 3 times the column vector 1, 2 plus 2 times the column vector 4, negative 7, I'm making these up as I go along, is a linear combination of the vectors 1, 2 and 4, negative 7 from R2. Okay. Let's take a look at another example. Let's say 3 times sine of x plus 2 times cosine of x. This is a linear combination of two vectors. Linear combination of sine of x and cosine of x. Sine of x and cosine of x are vectors from C negative infinity to positive infinity. They're continuous functions from the vector space c minus infinity to positive infinity. Okay, so it's kind of weird. Our vectors don't look like the ones from physics that you're used to. Vectors can be functions or matrices, all kinds of stuff. Okay, another definition. We have a definition of something called the span. The span of V1, V2, V3, all the way up to, say, V sub n. The span. And the span of a set of n vectors is nothing more than the set of every single linear combination of those vectors. It's nothing more than the set of all linear combinations of the vectors v1, v2, all the way up to v sub n. Okay, in more formal notation, it's the set of all v from the vector space v, such that v equals c1 v1 plus c2 v2 plus dot dot dot, all the way up to cn vn for some scalars c1, c2, all the way up to c sub n. The set of every possible linear combination of a set of vectors is called the span of the set of vectors. Okay. Now, with respect to what we just finished talking about for the last hour and 20 minutes or so, we get a special theorem about the span of a set of vectors. Theorem 2.5 from your textbook. Theorem 2.5 from your textbook. The theorem says that the span of a set of vectors v1, v2, all the way up to vn, what do you think? The span of a set of all linear combinations of a few vectors, v1 to vn, is a subspace of the vector space V. Okay? Keep in mind what's going on here. We have a vector space. We have a vector space, V. Vector space. I'd kind of like to make my vector space bigger here. We have V of vector space. Let me make it bigger. And inside that vector space, we have the span of v1 to vn. We have the span of a set of vectors of v1, v2, all the way up to vn from that vector space. Okay, well, the vector v1 itself is in that span. The vector, I'm using dots for the vectors, the vector v2 is in there. How can v1 be in the span of those vectors? Well, v1 equals 1 times v1 plus 0 times v2 plus 0 times v3 plus dot dot dot, all the way up to 0 times v sub n. So v1 is a linear combination of those n vectors, a very easy one. So the vectors themselves are in there, vn, and so is every linear combination, c1 v1 plus c2 v2 plus dot dot dot, where c can range through all real numbers, all scalars. Okay. In particular, all the scalars could equal what? 0. That means 0 is in there. So this set is not empty. Okay. So let's prove the statement that the span of v1 to vn is a subspace of V. So we start out with let v1, v2, all the way up to vn be in V a particular vector space. Okay, the span, we need a non-empty subset, so the span of V1, oops, not C1, V1, V2, all the way up to Vn is not empty, since 0, the 0 vector, which is 0 times V1 plus 0 times V2 plus dot, dot, dot. That's just a linear combination. The span contains all the linear combinations. In particular, it contains that vector, where all the scalars in that linear combination are 0. Since the 0 vector is in there, the span of V1 to V2 all the way up to Vn. You're used to a lot of writing in this section coming out. Lots and lots and lots of writing. Okay. 1. We need to show that the set that equals the span of the V1 to Vn is closed under the operations of addition and scalar multiplication. That's what we have to show for a subspace. So pick two things out of there, out of the span. Let U and V be elements of the span of V1 all the way up to Vn. Okay, I want to show that the sum of those two are in there. Well, since each one is in there, each of those U and V are in there, then U must equal some C1 V1 plus C2 V2 plus dot 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 plus Cn Vn. I'm going to use some notation that we're really familiar with to make that note, to make this vector a little easier on the eyes. It's the sum of all the Ci Vi's where I ranges from 1 to n. Okay, let V, or rather, since V is in the span, then V must equal some D1 V1 plus D2 V2. Remember, to be in a span means that that vector needs to be a linear combination of the V1 to Vn. That's nothing more than the sum of the Di Vi's. I ranges from 1 to n. I need to show that the sum of those two are in there. Well, add V1 plus V2. Sorry, not V1 plus V2. Add U plus V. U plus V is nothing more than C1 plus D1 V1 plus C1 plus D2 V2, blah, etc. I'm going to use the sigma notation to help us out with this. It's nothing more than the sum I goes from 1 to n, Ci Vi, plus the sum I goes from 1 to n, Di Vi. If you'd rather see this without sigma notation, take a look at the textbook proof. He does it without sigma notation. Okay, this is nothing more than Ci plus the sum Ci plus Di Vi. I goes from 1 to n. That's just another linear combination of V1 to Vn. If you need to see it without sigma notation, I'll write it. This is just C1 plus D1 V1 plus C2 plus D2 V2 plus dot 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 all the way up to Ci. Oh, no, it's not I. Cn, sorry, plus Dn Vn. That is just an element of the span of the vectors V1 to Vn. Don't get too lost in what don't lose what we're trying to do. We're trying to show that the span, the set of all linear combinations of a fixed set of vectors from a vector space, we're trying to show that that span, the set of all linear combinations, forms a subspace. I've just shown that I have closure under addition. Now I'm going to show that I have closure under scalar multiplication. I'm going to let U be defined as above. So let C be a scalar, and let's take C times U. C times U is nothing more than C times, I think I was using C's, C1 V1 plus C2 V2 plus dot 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 plus Cn Vn. I much prefer the sigma notation. CI, VI, I goes from 1 to n. Just use a distributed property we have for vectors. We can distribute constants into vectors. I goes from 1 to n, distribute. C times Ci, Vi. We have another property that allows us to rearrange the parentheses in multiplication. C, Ci, Vi. This is just another linear combination. Let's say Gi, Vi, I goes from 1 to n. That's just another linear combination of the VI's. So C's G1, V1 plus G2, V2 plus ... all the way up to Gn, Vn. That's just another element from the span. So I've shown that I have closure under addition and scalar multiplication. Done. QED. So the span of a set of a few vectors from a vector space forms another vector space, forms a subspace, okay, of the vector space. Okay, we have some terminology. The span of a set of vectors, V1, V2, all the way up to Vn, we just showed that it itself forms a vector space. It's a subspace of V. It is called, so this is definition, this is not a theorem, it's called the I'm going to write this in red, the subspace of V spanned by the V1 all the way up to Vn's. V3 ... all the way up to Vn's. It's the span, oh, that's the ugliest, Vn. Oops. The span of a set of vectors is called the subspace of V that's spanned by the V1 to Vn. Okay, now let's get to a specific example. We're getting a lot of, we're starting to build up a lot of the theory and notation and stuff. Let's let a specific, look at a specific example. Let's let V1 equal the vector 1, column vector 1, 2 from R2. Okay, from R2. Determine the span of the set of vectors, just V1, the set of all linear combinations of V1, the set of all linear combinations of V1. Okay, so the span of V1 is nothing more than the set of all V's that are in R2, the set of all vectors from R2, such that V is a linear combination. V is some linear combination of the vector 1, 2. Not a real exciting set, but it just really doesn't describe the set very well. We can see what R2 is. It's the XY plane with written as column vectors, points are written as column vectors. What does the span look like? Okay, well, let's get a little better of a look at what this set looks like geometrically. Let's pick something out of the span of V1. Let's let V equal XY, a column vector whose entries are X and Y, be inside of that span. Okay, that means that XY V is going to equal some linear combination. In this case, just some scalar multiple of 1, 2. Now let's invoke our knowledge of matrices. Well, if these two matrices are equal to each other, then the first component of the first matrix, first entry of the matrix, should be C times 1. And the second entry of the matrix X of the left-hand side should equal C times 2. That means X should equal C and Y should equal 2C, where C is just any scalar. Well, if you had Calc 3, these are just parametric equations. If you haven't had Calc 3, these are just parametric equations. Don't worry about it if you haven't studied parametric equations yet. Eliminate the C. So if X equals C and Y equals 2C, that means Y equals 2X. What is that? This is a line through the origin. So if the vector space is all of R2, then the line y equals 2x, this is the line y equals 2x, that is the span of the vector 1, 2. It's the set of all linear combinations of the vector 1, 2. So the span of this vector, the single vector 1, 2, is a line through the origin. So lines through the origin, this particular line through the origin, in fact, all lines through the origin, it turns out, this particular line through the origin is a subspace of R2. We looked at another line through the origin as a subspace of R2 when we began this lecture. It was the x-axis. It was a set of all points x, all column vectors x0. Okay, this is just one other line that goes through the origin. It also forms a vector space. Okay, let's take a look at another example. Let's, for example, let V, let's get away from R2, equal the set of all 2 by 2 matrices with real entries. Okay, that's a vector space. It's a subspace of the set of all vectors, m by n vectors. Okay, so the set of all 2 by 2 square matrices, that's V. Let's pick 3 vectors from M. Let's let A1 be the vector or let the matrix, the 2 by 2 matrix, whose entries are 1, 0, 0, and 0. A2 is 0, 1, 1, 0. A3 is 0, 0, 0, 1. I have 3 vectors from the set of all 2 by 2 matrices with real entries, that vector space. Let's determine, just like we did before, determine the span, the set of all linear combinations of A1, A2, and A3. Okay. Well, what is the definition of the span of these 3 vectors? It's the set of all A, the set of all vectors from our vector space, set of all 2 by 2 matrices with real entries, such that A is a linear combination of these 3 vectors. A equals C1, A1 plus C2, A2 plus C3, A3. Okay, where the C1, C2, and C3 are scalars. C1, C2, and C3 run through all possible scalars. Okay, let's get an idea what this particular subspace of V of the set of all 2 by 2 matrices looks like. Okay, so pick something out of there. Let's let A be in the span of these 3 vectors. A1, span of A1, A2, A3. Let's see what they look like. See what a typical entry element A looks like. Well, that implies that A equals C1 times 1, 0, 0, 0, where C1 could be anything, plus C2 times 0, 1, 0, 0, 1, 1, 0, plus C3 times 0, 0, 0, 1. Now let's perform this matrix arithmetic. This is nothing more than a matrix C1, C2, C2 on the, not the main diagonal, but the other diagonal, and C3. So I picked something out of the span of those three vectors, three matrices, and it must look like the matrices of this form. Do you recognize these matrices? C1, C2, C3 are just real numbers. All real numbers, any real number, arbitrary, like a constant of integration, they're anything. What do you notice about A transpose? A transpose is C1, C2, C2, C3. That's A. This set is nothing more than a set you've seen before. This set is the set of all, do you recognize them? 2 by 2 symmetric matrices. What we've shown is that the set of all 2 by 2 symmetric matrices is a vector space. How is that? Because we've shown that the set of all 2 by 2 symmetric matrices is made up of the span of these three vectors from the set of all 2 by 2 matrices with real entries. But the span of any three vectors from a vector space form a vector space themselves. They form a subspace. So you're starting to see, hopefully, what we're doing here. We're trying to make the things that we've talked about before, functions, matrices, vectors from physics, and a lot more stuff, a lot more structures. We're trying to make them vector spaces, things that satisfy those 8 properties, so they will enjoy all the properties of general vector spaces. We're going to develop a set of properties for vector spaces, and we're going to try to make a lot of the sets of objects that we've studied in previous math courses vector spaces, so they will enjoy whatever theory that vector spaces satisfy these particular examples, polynomials, continuous functions, matrices. They will enjoy all the theory that we develop for vector spaces. What we're doing is what mathematicians refer to as we're constructing a unifying structure for objects in mathematics. We're trying to put a lot of the objects that we've studied in a general framework of something bigger, and then the bigger thing's called the vector spaces, and then we develop a theory of vector spaces, and the end result is that those things that we studied before are themselves vector spaces, so they enjoy all the wonderful, rich theory of vector spaces. That didn't come out too well, but okay. Let's practice with the concept of the span of a set of vectors. Okay, so example. Let's see. I want to go here. Okay, part A is the column vector 1, 2, 3 in the span of the vectors -1, 1, 3, 2, 1, 2. This span is a vector space. It's a subspace of R3. How do I know it's a subspace of R3? Because I just finished proving that the span of a set of vectors is a subspace of a vector space. I have a question. The question is the vector from R3, if you've had Calc 3, the point 1, 2, 3, is it in the span of these two other vectors? That is, can it be written as a linear combination of these two vectors? If you missed what I just said there, we need a C1 and C2 such that, in order to answer this question, yes, we need a C1 and C2 such that that vector is a linear combination of those two vectors. The span of a set of vectors contains all the linear combinations of the vectors. Okay, so if I want some particular vector to be in there, that means I need to find real constants, C1 and C2, such that the vector equals C1 times the first vector in the span plus C2 times the other. Okay, well, let's get this out of a matrix equation and turn it into a set of scalar equations. This tells us that negative C1, I'm looking at the right-hand side, negative C1 plus 2C2, there's the sum of the first entries of the C1 V1 plus C2 V2. That has to equal 1. C1 plus C2, the second entries, must equal 2 when you add them up on the right-hand side. Add up the vectors on the right. It also means that 3C1 plus 2C2 has to equal 3. Look at what just happened. This is kind of a monumental thing to happen right here. I've replaced the question, is a vector in the span of a set of vectors, with a system of equations. This is going to happen a lot in our course. And the answer to the question depends on whether this system of equations has a solution or not. Okay, I'm going to use the Gauss-Jordan elimination method on this. And I did all the work for us, so we don't have to do any kind of row operations. I'm going to produce the row reduced echelon form using elementary row operations. And what that turns out to be is 1, 0, 0, 0, 1, 0, 0, 0, 1. So the system has no solution. The system has no solution. This says 0 C2 needs to equal 1. There's no solution. No solution. That means there do not exist constants C1 and C2. Okay, this is very important. That is, there does not exist C1 and C2 such that 1, 2, 3 is C1 times the first vector plus C2 times the second vector. We cannot possibly find constants to make this work. The other one was 2, 1, 2. That means 1, 2, 3. That is 1, 2, 3 is not in the span of those two vectors. I mentioned a few minutes ago, that what you just saw here is going to be very common to us. What you just saw is we replaced a question about vector spaces with a system of equations. And our answer to the question about the vector spaces depended on whether a system had a solution or not. In this case, I used brute force to solve the system and found that the system had no solution. Okay. Conclusion, that there are no constants C1 and C2 that'll put the point 1, 2, 3 in R3 or the column vector 1, 2, 3 in this span. So it's not in there. Okay. B. Is the point 1, 5, 15 in the span? In the span of the vectors -1, 1, 3, 2, 1, 2. Okay. Okay, so we need two constants. We need C1 and C2 such that 1, 5, 15, our particular vector is C1 times one of the vectors plus C2 times the other one. That's what it means for one vector, the vector, column vector 1, 5, 15, to be in the span of those two vectors. But if we rewrite this vector equation as a set of scalar equations, this says -1 times C1 plus 2 times C2 needs to equal 1. C1 plus C2 needs to equal 5, and 3C1 plus 2C2 needs to equal 15. Well, I used the Gauss-Jordan elimination method again. This is why we studied, but one big reason why we studied solving systems of equations earlier. Real big reason why. Produce the reduced row echelon form, which always exists and is always unique. There's only one reduced row echelon form. And that tells us that we have a system that has a unique solution. C1 equals 3, C2 equals 2. So yes, so the point, was it 5, 15, 1, 5, 15, 13? 1, 5, 13, I think that was what, that was 1, 5, 15. I wrote 13 in this one, the augmented matrix. I'll fix it. It says the column vector 1, 5, 15 equals 3 times -1, 1, 3 plus 2 times 2, 1, 2. Not only do we have the answer to the question, does this vector 1, the column vector 1, 5, 15 lie in the span of those two vectors? Yeah, not only that, I found the actual constants that put it there. If you were to perform this arithmetic, it should work. Yeah, I did the arithmetic on the right hand side. I wasn't sure it was going to work, but it did. So yes. So yes, 1, 5, 15 is in the span of those two vectors. Okay, -1, 1, 3, 2, 1, 2. Ultimately, and you don't have to concentrate too much on this statement, but we're doing a lot of work with spanning sets and so forth, and you're probably wondering why. Ultimately, we're headed toward the idea of taking a complicated structure and writing it as a linear combination of simpler pieces, simpler vectors. We're looking at taking vectors in different vector spaces and being able to write them as a linear combination of a few simple vectors. In this case, the column vector 1, 5, 15 can be written as a linear combination of these other two somehow They don't really look simpler, but somehow simpler, or at least not more complicated looking vectors. Okay, we're looking at representing vectors as linear combinations of simpler vectors. Okay, can't say too much more about that, except if you had Calc 3 or physics, we can write, let's say this is just for those of you who've had Calc 3 or physics. We can take the vector 5, 3, 2 in R3. This is Calc 3 notation, and we could write them at this vector as 5 times I plus 3 times j plus 2 times k. Okay, so this vector is in the span of the vectors I, j, and k. And this was really, really important that we're able to do that. Those I, j, and k are called the standard basis vectors, if you'll recall, if you had Calc 3 or physics. And this is really, 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 really important. Okay, if you haven't had Calc 3 or physics, don't worry about it. Right now, just concentrate on what we're doing. Yeah, and have faith that this stuff has more meaning in your future as a STEM major than you probably have any idea. Okay, this stuff's real important. It's so important that I want to look at more examples, a couple more examples. Okay, so example is, let's say, part A is x squared plus 2x in the span of the set of vectors x2 minus x squared, x2 minus x squared minus, I keep saying x2, x squared plus x plus 1, x squared plus 3x plus 2. Okay. Is that true? So what vector space are we in? What's the master vector space? What's the big vector space that this span? The span of these three polynomials is in what vector space? It's in P2. Okay. These vectors are in P2, the set of all polynomials of degree less than or equal to 2. What is that set? What's a sort of really easy to understand idea of what the set P2 is? P2 is the set of all polynomials of degree 2 or less, degree 2, degree 1, or 0. So it's the set of all quadratic functions, second degree polynomials, linear functions, first degree polynomials, or horizontal lines, 0 degree polynomials, y equals a constant. Okay, so the question is this parabola, x squared plus 2x, in the span of these three parabolas? Is it a linear combination? Can I make this one parabola a linear combination of these others? Okay, so we need C1, C2, and C3 such that x squared plus 2x, our vector, is equal to C1 times the first vector plus C2 times the second vector plus C3 times the third vector. And these vectors, polynomials, have nothing to do with systems of equations. Nothing. They're polynomials. But watch what happens when we translate this question into what it really amounts to. Let's get rid of, or not get rid of, let's simplify on the right a little bit. Let's gather powers of x. This means C1 times x squared plus C2 times x squared plus C3 times x squared Now gather the powers of x together. X is the first. So plus negative C1 plus C2 plus 3C3. That's the coefficient of x. Now gather the constant terms together. C1, there's no constant term for C1. C2 times 1, C2 plus 2C3. That's on the left. Right, rather. On the left, you have x squared, 1x squared plus 2x plus 0. Well, if this equation is supposed to hold true for all x values, no matter what x, then the coefficients on the right have to equal the coefficients on the left. You did this sort of thing when you did partial fractions in not partial fractions. Oh yeah, it was partial fractions in calculus. C1 plus C2 plus C3 equals 1. Minus C1 plus C2 plus 3C3 equals 2. I'm setting the coefficients on the left-hand side equal to the coefficients on the right. C2 plus 2. Look what just happened. I replaced the question, is a particular quadratic function in the span of 3 other quadratic functions, with, is there a solution to the system of equations? This is going to happen a lot. So, well, one way to do this is to use brute force. Try to solve the system. Solve the system. Sometimes we're not going to need to solve the system. How could that be? Well, we have connections between certain systems, and this one is a square system, 3 variables, 3 equations. We have a connection between the system and determinants of the coefficients and stuff, so that comes up soon. But for right now, let's just use brute force, which I did. I entered the augmented matrix in my calculator. I accessed RREF, and I got this. This says there's no solution. This says that 0 times C3 equals 1. No solution. No solution to the system. There are not constants. There are not three constants. There do not exist. I'm going to use the symbol. There do not exist C1, C2, and C3 such that that whole long equation holds true. And I copy and pasted it off camera. This is what we needed. We needed our vector x squared plus 2x to be a linear combination of those 3 vectors inside the span. Okay, we cannot find three constants, so no. Okay, so no. X squared plus 2x is not in the span of those 3 vectors. Okay. If we had a solution to this system, the answer would be yes. And that allows me to go up to my example and remove the part where I wrote A, so we don't have to look at a B. Okay, let's see where we want to go from here. Okay, we're rounding out the last corner here. We're going to head through the last lap of this section now. What I'd like to do is take a look at the concept of spanning as a verb now. And this is a little difficult for students at first. We've used the word span, or the concept of span, as a noun. The span of a set of vectors is a subspace of a vector space. It's a set of all linear combinations of a few vectors. Now, I want to look at the possibility of having the word span as a verb. And here's what I'm talking about. we say that the vectors v1, v2, v3, all the way up to vn, and here's where we're using the word span as a verb. They span V. I'm not talking about the span of V. They span V if the subspace that they form by spanning, if the noun, the span of V1, V2, all the way up to Vn equals the whole vector space V. Now look at the diagram above. We showed earlier that the span that's supposed to be that part of the vector space V in the little blob in the puddle there, the span is a subspace of V. It doesn't necessarily cover the whole space V, but if it does, if the whole vector space V is completely covered by the span of V1 to V3, V1 to V3, V1 to Vn, then we say those vectors V1 to Vn span V. Okay. In other words, V1, the vectors V1, V2, all the way up to Vn span V if every vector in V is a linear combination, of those vectors V1 to Vn. Okay, so once again, earlier, the span of a set of vectors is just that part of the vector space V that is covered by linear combinations. That is, the span of a set of vectors V1 to Vn is just a set of all C1 V1 plus C2 V2 plus plus Cn Vn. That portion of the vector space that contains all the linear combinations. Now, if that portion of the vector space that contains all the linear combinations equals the whole vector space, then you have those vectors tending to span as a verb the vector space. They completely cover the vector space by linear combinations. If those set of vectors span V if every vector in the big master vector space is a linear combination of those. Okay, hopefully this will become a little more clear with our last examples here. So for example, do V1 equals 1, 0, so we're in R2, and V2 equals 0, 1. Now, if you've had Calc 3 or some physics, this is going to be not so bad for you. Do these two vectors span R2? Do they completely cover R2 by linear combinations? Is every vector in R2, is every point in the xy plane a linear combination of these? If you've had Calc 3 or physics, you know the answer to this. Okay, do V1 and V2 span R2? We need to determine if every vector, let's say V in R2, is a linear combination of V1 and V2. Okay. Okay, so let's see if this is true. Let's pick something from R2. Let's let V equal AB be an arbitrary point from R2. Okay, now watch this. As if you're not going to watch this if you're not watching already. V, which is A with the column vector AB, I can tear that column vector apart. Okay, remember, our operations are still the ordinary operations of addition and scalar multiplication. So AB as a column vector is A0 plus 0B. But I have this through scalar multiplication. I can write this as A times 1, 0 plus B times 0, 1. But 1, 0 and 0, 1, those are the vectors V1 and V2. So I've shown that any arbitrary vector V from R2 is a linear combination of V1 and V2. Okay, so yes. So yes. Yes to what? V1 and V2 span R2. Every point in R2 is a linear combination of 1, 0, and 0, 1. That's what it means to span R2. Okay. Let's take a look at another example. Same vector space, R2. So do V1 equals 1, 1. And V2 equals 2, 0, do those two vectors span R2? Can every point in R2 be written as a linear combination of these two vectors? Okay, just like before, we need to determine if every vector in R2 is a linear combination of V1 and V2. Oops. So we need to determine, I just copied and pasted the statement from the last example. We need to determine if every vector in R2 is a linear combination of the vectors V1 and V2. Okay, we need to determine if for every V in R2 there exists constants C1 and C2 such that V equals C1 V1 plus C2 V2. So just as we did in the last example, let V equal the vector, column vector whose entries are A and B. Okay. Okay. And assume that, let's say, V equals C1 V1 plus C2 V2. And what does that mean? It means our arbitrary vector, let's assume that we do have a linear combination. So AB column vector is equal to C1 times the vector 1, 1 plus C2 times the vector 2, 0. This translates into a system of equations. C1 plus 2C2 equals A. C1 plus 0C2 equals B. Okay. Well, it's a little rough to use a calculator. In fact, it's impossible to use a calculator to use the Gauss-Jordan elimination method. However, let's take the determinant of the coefficients. The determinant of 1, 1, 2, 0. We could also solve the system just through brute force, but the determinant of the coefficients is -2, which is not 0. Okay. So if the determinant of the coefficients is not 0, that implies that the system, this is some theory from before, the system has a unique solution. If you don't remember this theorem, it's okay. I'm reminding you of it, and we're going to be seeing this same process over and over and over again. If you have a square system, a system of same number of equations and unknowns, and the determinant is not 0 of the coefficients, that means we have a unique solution. That implies that the solution was the constants C1 and C2 that we were looking for. So this implies that there exists constants C1 and C2 such that V equals C1 V1 plus C2 V2. So yes. Okay, the question is, do the two vectors V1 and V2 span R2? Yes, I found constants that make V a linear combination of the two vectors. So V1 and V2 span R2. Every vector in R2 is a linear combination of these two vectors. Okay. Okay, we have one more example and we're done with this long section. So for example, determine if three vectors, x3, I keep doing that, x cubed plus x squared, I think I'm getting tired, x cubed plus x squared plus x, four vectors, x plus 1 and 1. We have four vectors. Determine whether these vectors completely span P3. Set of all polynomials of degree 3 or less. This means we're trying to determine if every cubic polynomial, quadratic polynomial, or linear polynomial, or constant polynomial can be written as a linear combination of these three vectors. If you miss that, the problem is that we need to determine if for every v in P3, for every cubic, quadratic, linear, or constant polynomial, there exists constants C1, C2, and C3. Actually, hang on a second. Sorry, and C4, such that V equals C1 V1 plus C2 V2 plus C3 V3 plus C4 V4, where the V1, V2, V3, and V4 are the original polynomials. So x cubed plus x squared is V1, x squared plus x is V2, V3 is x plus 1, and V4 is a constant polynomial 1. Oops, 4. Okay, so let's see if we can do this. Well, let's pick a V out of P3. Let V be in P3. That means that V is going to be some ax cubed plus bx squared plus cx plus d. Remember, P3 is a set of all polynomials of degree 3 or less. That means V will have this form. It'll be some constant times x cubed plus some constant of x squared plus some constant of x plus some constant. Constants A, B, C, and D can all be 0, or they can a couple of them can be 0. A could be 0, and B, C, and D could be non-zero constants, in which case we'd have a quadratic, etc., etc., etc. Okay, so we need to see if we can find four constants, C1, C2, C3, C4, so that this polynomial can be written as a linear combination of the given 4 polynomials. So let's see what that amounts to. It means that we need to find 4 constants, C1, C2, C3, and C4, such that our arbitrary element of P3 is a linear combination, C1 times the first polynomial, x cubed plus x squared, plus C2 times x squared plus x, plus C3 times x plus 1, plus C4 times 1. We need to see if we can find constants C1, C2, and C3 and C4 that will make this work. Well, let's translate this vector equation, vectors are polynomials now, into a system of equations. So we'll gather the constants, the powers on the right, and set the coefficients on the powers on the right equal to the coefficients on the left. Okay, if you missed what I just said there, I don't blame you. On the right, we can write this as C1 times x cubed plus, now look at the coefficients of x squared, C1 plus C2 times x squared. Now let's take a look at the coefficients of x, plus C2 plus C3 x. And let's look at the constant coefficients, plus C4, it's all by itself. And that needs to equal the ax cubed plus bx squared plus cx plus d. Well, this equation has to be true for all x, independent of x. So the coefficients on the right of x cubed, the coefficient on the right of x cubed should equal the coefficient on the left of x cubed. So that says that C1 needs to equal A. It also says that C1 plus C2, the coefficient of x squared on the right, should equal B, the coefficient on the left of x squared. It also says that C2 plus C3, the coefficient of x on the right, should equal C, the coefficient of x on the left. And finally it says, I think I've screwed up the coefficient, the constant coefficient. I think it should be, I'm going back up, I think it should be C3 plus C4. Yeah. So C3 plus C4, the coefficient, the constants, should equal D. Now we have a system of 4 equations and 4 unknowns. The determinant of the coefficients, the determinant of 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, and 0, 0, I'm stating these column-wise, 0, 0, 0, 1. That determinant I computed in my calculator is 1, which is not 0. That implies there exists a unique solution. That implies there is a unique solution to the system. But the variables in the system were the constants we were trying to find. That implies that there exist constants C1, C2, C3, and C4 such that the arbitrary vector from P3, V, is equal to C1 times V1 plus C2 times V2 plus C3 times V3 plus C4 times V4. That means those three vectors, V1 to V4, span P3. So V1, V2, V3, and V4 span P3. Every vector in P3 is some linear combination of those four vectors. Okay. Now again, this was a very, very long section. I would imagine that it's going to take quite a bit of time to get through the homework on this section, so I would get started on it right away. You can always refer back to video lecture to determine the difference between, and this is probably going to be the hardest parts of the lecture, span as a verb and span as a noun, spanning span of a set of vectors, whether or versus whether a set of vectors span a vector space. 30 years in, and I still have a hard time saying the two different scenarios. In any case, this ends this video segment in a kind of awkward way, and I am looking forward to talking with you all again.